Section 3.5, implicit differentiation. Now, up to this point, we have differentiated functions that were all written in the form of y equals. So I had a function y equals something in terms of x. Now, make sure we're clear on the language here. If I keep harping on the language, the terminology, the notation is critical to a lot of this. So remember basic function language, or basic language of equations. When I say that y equals x cubed, for example, as I have in this function, we say here that y is a function of x. Y is explicitly written as a function of x. Or when we say f of x equals x cubed plus 3x squared plus 2x plus 1, that is a function of x. F is a function of x. Or we say it is explicitly written as a function of x, because x is our input and then y, or f of x, is the output, right? And so far we've only dealt with equations or functions that were explicitly written in terms of x, right? And then we differentiated that function with respect to x, and that gave us dy dx. Well, what happens if I have an equation like x squared plus y squared equals 1, which you may recognize as the equation of the unit circle? That equation is not written explicitly as a function of x, right, in that y equals form. And so in other words, what we would like to be able to do to take an equation and put it in an explicit form would be solve it for y. So put it in that y equals form and hopefully obtain a single function or a single equation that would represent the output as a function of the input. Y is a function of x. But you could solve that equation for y. We could subtract x squared. I get y squared equals 1 minus x squared. And then we take the square root of both sides, and we end up with y equals plus or minus. Remember your plus or minus in front of that square root. Plus or minus the square root of 1 minus x squared. Now, I'm able to solve that equation for y, sure. But notice there's two equations there. There's a positive and a negative square root. There's two different equations that you would then have to work with. So yeah, I could solve that equation for y, and I could say, okay, now let's differentiate that function or that equation, but I would have to differentiate each of those separately. There's a positive square root of 1 minus x squared and a negative square root of 1 minus x squared. So it's doable, but you can kind of see how that could be a little bit cumbersome. If I end up having an equation that I would solve for y, maybe I could end up with multiple equations. Y equals, okay? And then you'd have to differentiate each one of the individual equations. So it can be done in some cases, but a little bit cumbersome. And also, this is what we call an implicit equation. Right? So instead of saying that our function is explicitly representing y as a function of x, there's an implicit equation here that involves x and y. There's a relationship between the two, but I can't just solve that equation and get a single explicit representation of y as a function of x. So first of all, the difference between those two terms, explicit versus implicit. Now, if you look at the next equation that I have, x squared minus 2xy plus y cubed equals 38. Give that a shot and try to solve that for y. Good luck, because it can't be done. All right. And so you run across equations like this where maybe it's very difficult to solve for y, or in a case like this, it's not even possible to solve that thing and put it into a single equation, again, in terms of y equals some function of x. Okay? So that's the idea between explicit versus implicit. An explicit equation or an explicit function, I'm able to represent the output variable y as a function of x in terms of a single equation. Versus an implicit equation where I can either I can solve it for y and represent it using multiple equations, not just a single equation, or in some cases you can't even solve for y and explicitly represent that as a function of x. So here's the issue then. If I can't write the equation in terms of y equals, like we have in the first two, in those explicit equations, x cubed and the function f of x, how do we differentiate? How do we find dy dx? How do we find the change in y with respect to the change in x if I can't isolate the y on one side? So this is where implicit differentiation comes into play. So what we do then is, instead of Like we would take y equals x cubed and we say, okay, find dy dx, and I use my power rule and I get dy dx equals 3x squared. So in this case, for an implicit equation, we're not just going to differentiate one side, we're going to differentiate both. All right, so we treat the derivative as an operator. You know, we talked about that when we mentioned derivative notation or differentiation notation. And I said that ddx, and that we also saw that big D notation. We said that those were differentiation operators. So, I mean, so you can treat those just like operators, just like operations, and you can perform a differentiation process on each side of your equation. So if I have the left side equal to the right side of an equation, then the derivative of the left side has to equal the derivative of the right side. So you can treat it just like any other operation that you can perform to both sides of an equation. Now, before I continue with this, I will say this. Implicit differentiation is not a process that has to be or can only be applied in certain situations and not others. In other words, implicit differentiation can be applied to any equation or any function, even the ones that are written explicitly. It's just we don't talk about implicit differentiation here because if you take the derivative of both sides of this equation, the derivative of the left side is dy dx, right? And then the derivative of the right side, the x cubed sine x, overlook my sine x, the x cubed sine x, then we would differentiate that normally, right? Product rule and so forth, okay? But we also differentiate the left side at the same time, and the derivative of y is y prime, or dy dx, right? It's just a lot simpler when we have the equation written explicitly, y as a function of x. So implicit differentiation can be used to differentiate any equation or function. It's just absolutely necessary in a case like those other two equations where either I can't solve for y, or by solving for y I end up with multiple equations, so maybe it's just simpler to leave it in its original form, x squared plus y squared equals 1, and then apply this its implicit differentiation process. All right, so again, what does the implicit differentiation say? It allows us to differentiate both sides of the equation with respect to x, and this is again what we keep harping on in terms of the terminology. You've got to be clear with this. Now we're dealing, we have multiple variables involved in our equations. We have x's and we have y's, or whatever the variables happen to be. So when you're differentiating, typically we have y equals, we say we're finding dy dx. We're differentiating with respect to x, right? Change in y with respect to x. Here, I could differentiate with respect to x. I can even differentiate with respect to y. It doesn't matter. I could pick either one of the two variables to differentiate with respect to. Now, normally we do differentiate with respect to x because we are trying to find dy dx, or y prime, the derivative of our function, which gives us the rate of change of the function. Right? Remember, that's the whole deal with the derivative. It's giving me the slope of the tan line to the curve, and it's giving me the rate of change, or the slope of the curve. So that's why we're always finding y prime, or dy dx, change in y with respect to change in x. But mathematically, we could just as easily find dx dy, the change in x with respect to the change in y. I'll give you an example with one of those here in a bit. But I find the biggest deal with implicit differentiation, it's the notation and the language. So, when we talk about y as a function of x, what does that mean? When we talk about y prime, or dy dx, what does that mean? You've got to be clear on this notation and exactly what that notation represents. So we're differentiating with respect to x. So let's say, for example, let's find dy dx by implicit differentiation. There's our equation, x squared plus y squared equals 1. Go ahead and work it up. I did a little more detail over here. Now, when you're using implicit differentiation, notice the first step. I took our equation, x squared plus y squared equals 1, and I then showed that I am differentiating this equation with respect to x. So I take d dx of both sides, so the derivative with respect to x of the left side of the equation, the derivative with respect to x of the right side of the equation. Because like I said, you could just as easily here look for d dy. And I'll talk about that again in another example later on. So you should automatically, in your first step, if you are using implicit differentiation, you need to indicate what you are differentiating with respect to. All right, that'll be a point deduction if you don't make that statement. So then we go through our differentiation process. Now remember, here's where it's all about what are you differentiating with respect to. So the first thing we run across is x squared. So the derivative of x squared, well, I'm differentiating with respect to x, so that's normal differentiation. The derivative of x squared with respect to x is 2x. But then here's where things get a little different. I then have to differentiate y squared. Now this again is where you have to be careful of the language, the notation, the terminology. What is y? Y is a function of x because we are treating this equation still with x as our input, y as our output. We're differentiating with respect to x. I want to know how y changes with respect to x. So that's why we say we're finding dy dx. Now looking at y squared, this is where chain rule comes into play because y squared, and y is the base of that power function. Y is a function of x. So how do we differentiate a power function? We use the power rule. The derivative of y squared is 2y. But then we have to differentiate the base. What is the derivative of y with respect to x? Well, it's dy dx, or y prime, if you prefer. And I'm going to do it both ways. I mean, which notation you use, ultimately I think y prime is probably preferable just because it's less congested. But you can use dy dx, you can use y prime, whichever you prefer, I don't care. I ultimately end up using y prime most of the time just because it's less cumbersome, less congestion in my equation. But you can use dy dx, that's fine. Let me mention this too while I'm thinking about it, because if you go back to x squared, because I mean this kind of gets lost too. So when we talk about power rule, so when I differentiate x squared, that's a power function. And so we use power rule, which is 2x. And then if we do the same thing we did with y squared, I'd say, okay, well then you have to multiply by the derivative of the base, right? Because that's what we did here. We said power rule, 2 times y to the first, times the derivative of the base with respect to x, which is dy dx. Here, if I do x squared, 2x is its derivative, times the derivative of the base. Well, what's the base? The base is x. And what's the derivative of x with respect to x? Well, that's 1, right? So that's basically, it's this. It's the derivative of x with respect to x, which is 1. So, you're still using chain rule, even with something as simple as x squared. It's just with x squared, since the base of the function is x, its derivative is 1, we don't bother writing it. So it's still chain rule. That gets lost in this, I think. We don't emphasize that enough. We do talk about it a lot more in the case like y squared, because y is a function of x, I have to differentiate y, whose derivative would be dy dx. Okay? And if you come to grips with that, then implicit differentiation, it should be a piece of cake. And I think it tends to work out pretty well as long as you comprehend and you get comfortable with the idea of, again, what am I differentiating with respect to what? Right, so when I differentiate x squared with respect to x, I get 2x. When I differentiate y squared with respect to x, I get 2y times the derivative of the base, which is dy dx. All right. And then the right side, there's the derivative ddx of 1, which, that doesn't change. We said the derivative of a constant is going to be 0. I don't care what you differentiate with respect to. If it's a constant function, it's a constant function. It never changes. So its derivative is 0. Now, once you're finished with your differentiation, then it's all about solving for dy dx. Okay? Now, let me mention that I broke this down over here. So, again, the ddx of y squared, and if you find this helpful, because this goes back to when we talked about chain rule and the whole composition of function things. So when I take the derivative with respect to x of that function y squared, we said chain rule says you have to differentiate the outer function, which is the y squared, with respect to y, which is the input variable, into that function. But then you have to multiply the base or times the derivative of the base with respect to its input variable. And since again y is viewed here as a function of x, then I differentiate y with respect to x. So there's the dy of y squared. I'm differentiating y squared with respect to its input variable, which is y. But then I have to multiply times the derivative of that base with respect to its input variable, which is x. And then if you notice again, algebraically, I tell you, this stuff works out algebraically. You can divide out the dy, and what am I left with? I'm left with ddx of y squared, right, which is what we have there. And then you do each of the differentiations as indicated. So with respect to y, the derivative of y squared is 2y. And then with respect to x, the derivative of y is dy dx. Okay. Yeah, and I know it looks weird. It looks kind of strange when you first start with it, but that's the gist of it. I mean, so if you can come to grips with what's happening there, then implicit differentiation should be a piece of cake. Now, of course, this is all going to be in conjunction with everything else we've talked about. So you still have all, once you decide that you're going to use implicit differentiation, you still have to follow all the other processes. Product rule, quotient rule, different types of functions, power functions, trig functions, etc., all that's in play, So implicit differentiation is a process. All right, so then once we have all the the differentiation done, then let's take that equation and solve it for dy dx, because remember, that's what we want to find. Right? Ultimately, we still want to know what is the change in y with respect to the change in x. What is dy dx? So let's solve it for dy dx. So that's this equation. Right? So I'm just going to first subtract 2x, and I've got 2y equals dy dx. 2y dx equals negative 2x. And then I divide it by 2y. And so I get dy dx equals negative 2x over 2y, or simplifying, I've got dy dx equals negative x over y. And there's our derivative. Now, notice a couple of things here, of course. Again, that's dy dx. That's still changing y with respect to x. The main thing to notice is, with our explicit equations, all the ones we've done up to this point, where we had y equals, right, and then all the x stuff was on the right side, and then we differentiated the derivative y prime, or dy dx, was also a function of x. Notice in this case, dy dx is not just a function of x, it's also a function of y. So not only does the change in the x value dictate the derivative, but also the y value. Let me show you this just for why that happens. What's the deal there? So remember, this was the equation of the unit circle. So think about this. If I draw a unit circle here, right, that's our circle centered at the origin with a radius of 1. So notice what's happening here. If I want to know the change in y over change in x, the dy dx, if you pick an x coordinate for a point on this circle, let's say I was interested in the derivative right at that point. It has an x coordinate, right? But notice there's another point that has the same x coordinate. There's a point down here that has exactly the same x coordinate. And so when we say dy dx, which one are you talking about? I want to know the change in y with respect to x at what point? Because I've got 2 points that have the same x coordinate, and the slope of the tangent line is different in each case, right? The one at the top is a negative slope, the one at the bottom is a positive slope. So that's where this would come in, right? So not only do I have to tell it which x coordinate, or the x coordinate of the point I'm interested in, but also the y coordinate, because it matters in this case. Okay? So, that's typically a situation for implicit differentiation. I don't have a function there, right? I mean, remember, a circle is not a function, doesn't pass vertical line tests. So, you've got to be more specific as far as which point you're finding the derivative at, right? The rate of change at. All right, but that's the idea, that's kind of broken down in minute detail. From here, again, I'm just going to do some different examples, using implicit differentiation, and then wrapping that up with all these other processes that we've talked about up to this point. Okay? So, number 2 that I squeezed in right there, I've got the equation y e to the y equals x. And I'm looking for dy dx. Now again, keep this in mind when we say differentiate the equation, the implication is I'm finding dy dx unless otherwise noted. Like I said, I'll give you an example here in a minute where we're finding dx dy instead of dy dx, because it's all about which one is being treated as the input variable and which one is the output variable. So when we say dy dx, we're treating y as a function of x. All right, so again, notice my first step. I indicated that I am differentiating both sides of this equation with respect to x. Make that a habit. So I've got ddx of y e to the y equals ddx of x. And then we'll go through our differentiation process. Now this is where, again, you're just recognizing the processes that you're going to have to follow. All right, so when I differentiate y times e to the y, well, obviously, there's a product there, so I have to use product rule. Don't forget product rule, people. I see it so many times where we forget that there's a whole product rule that has to be employed. The derivative of a product is not just the product of the derivatives. There's that whole first derivative of the second plus second times the derivative of the first thing. So make sure you are recognizing there's a product and I'm following product rule. So what does the product rule say? Well, it says take the first, which is y, times the derivative of the second, which is e to the y, with respect to x, plus the second, which is e to the y, times the derivative of the first, with respect to x. Now I went ahead and took care of the right side because the derivative of x with respect to x, right, ddx of x is 1. So here's our first d second plus second d first equals, and then the right side I was able to go ahead and take care of. And like I've said before, when you're using these different processes, product rule. And I think especially even more so when you're doing this implicit differentiation, so you can keep everything straight, write it out. And now let's go in and find each of the indicated derivatives. Right? So there's our y times the derivative of e to the y with respect to x. So again, I'm treating y as a function of x. I'm differentiating an exponential function base e. What is the derivative of exponential function base e? It's the function times the derivative of the exponent. All right, that's the basic process for any exponential function base e. So the derivative ddx of e to the y would be the function e to the y times the derivative of its exponent, which is y. And we're differentiating with respect to x, so just as before, the derivative of y with respect to x is dy dx, or y prime. If you want to use prime notation, use prime notation. I'm going to use that in my next examples, I think. So then plus, we have the e to the y times the derivative of y. Now again, that's the derivative of y with respect to x. So what is d dx of y? It's dy dx. And notice it's just basic notation there. That, you know, just look at the way that it's written. It's d dx times y, which is dy dx. It's all algebraically correct notation. And again, there's equals 1, which you already have. So now I'm done with the derivatives. Once we're finished differentiating, then we solve for dy dx. So we want to put this in the form of dy dx equals what? So the rest of this, once you're finished with differentiation, as we've said before, it's all algebra from this point forward. I'm solving for dy dx. So on the right, left side, I have those two terms that both have a dy dx. So what I did first was I just factored out the dy dx out of those two terms, which leaves me with y e to the y plus e to the y. And the right side is still just equals 1. And then to isolate dy dx, we go ahead and divide by that y e to the y plus e to the y to get our derivative. And notice again, in this case, actually, dy dx doesn't even depend upon x at all. Dy dx actually depends upon y. Okay? But that's the equation for dy dx. Number 3, question we've dealt with many times, right? Find the equation of the tan line to the curve x squared plus 2xy minus y squared plus x equals 2 at the point 1, 2. And so, of course, our initial step or process here, if I want the equation of the tan line, what do I have to first find? I have to find the slope of the tan line at that point, right? So here's our equation. I'm going to differentiate with respect to x, because again, we want the slope of the tan line, which is dy dx. So I'm going to ddx both sides of that equation. ddx of the left side, ddx of the right side. And then we'll do our differentiation. Now again, I'm differentiating with respect to x. So the derivative with respect to x of x squared is still just 2x. Right? Times the derivative of the base, but the base is x, whose derivative is 1. So we don't bother writing that. But it's still basic chain rule. Now, the 2xy, there's a product there. I've got 2 times x times y. I'm not so concerned about the constant 2 as I am the x times y. So I'm going to treat my first function as 2x times the second function, which would be y. All right, so again, recognize there's a product, so I have to use product rule. So I'm using 2x as my quote-unquote first function and y as my second function. So when I differentiate, right, it's first times the derivative of the second. Now I went ahead and used y prime this time instead of dy dx. Again, like I said, that's just purely your preference. Just be neat. Of course, you don't want to misinterpret or look at a y prime and accidentally as y. So that's our first derivative of the first function, which is 2x, times the derivative of the second, which is y prime, plus the second, which is just y, again, times the derivative of the first, which is 2x. All right. So maybe let me make a note over here. So for that chain product rule, I'm treating the 2x as the first function, and I'm treating y as the second function. All right, so when we say our first d second plus second d first, okay, then we have minus y squared. So again, the derivative of y squared with respect to x, there's a chain rule. Derivative of y squared, power rule, is 2y times the derivative of the base, which is y, so its derivative would be y prime, plus the derivative of x equals the derivative of 2, the constant, which is 0. All right, so we're starting to come across some of the same types of functions and derivatives. Okay. Now again, I'm done with the differentiation now. All that's left is to solve it for, in this case, y prime, because I use that notation. Now, the first thing I always do after these, and you know, you'll see this as you deal with these equations that are a little bit more complex or have a lot more parts to them. Once you do all the differentiation stuff, then maybe just clean it up a little bit first and then worry about solving for y prime. So I just went ahead and I rewrote a little bit. I left, you know, that was fine, 2x. I've got this plus 2xy prime plus 2y, so I just went ahead and wrote that as we would normally write that. Minus 2y, y prime plus 1 equals 0. So there wasn't much to do with this one. I just went ahead and rewrote the y times 2 as 2y. So I do recommend maybe just first clean them up, and then we'll solve it for y prime. Okay. And I've got a y prime here. I've got a y prime here. So let's keep those two terms on the left side. So that's 2xy prime minus 2y y prime. And I went ahead and brought everything else over to the right. So I subtracted 2x, subtracted 2y, subtracted 1. Now again, all I'm doing now is just solving an equation for, in this case, I'm solving it for y prime. That's all we're doing at this, from this point forward. Basic equation solving. So once I have the y prime terms on one side, then we'll factor out the y prime. All right. So pull out the y prime, and that leaves me with 2x minus 2y equals that right side. And then lastly, divide by whatever that factor is. So y prime, then I'm dividing by 2x minus 2y, and I get this. Okay. Now I want to show you just a little bit of algebra. I'll remind you of a little bit of basic algebra with some of this, because like we keep saying with these, once you actually do the process, perform the process, the differentiation, then there may be some rewriting that would have to be done. Right? Now there's nothing wrong with what I have there. That's perfectly fine. You know, if you put that as your derivative, nothing wrong. Some people may have an issue with the fact that the term in the numerator, the numerator of the fraction is negative. So again, there's no issues with that. That's algebraically perfectly fine. But you may see something like this done. What if we were to factor out the negative out of the numerator? So I've got negative, pull out the negative. I've got 2x plus 2y plus 1 if we factor out the negative. Over 2x minus 2y, that hasn't changed. And then remember, you could also then take that factor of negative 1 and put it in front of the fraction, and I've got negative 2x plus 2y plus 1 over 2x minus 2y. You may also see this done to where they then distribute it in the denominator so that you're eliminating that negative altogether. And if you distribute that negative into your denominator, right, if you take it and distribute it through here, that would give you negative 2x plus 2y, which is 2y minus 2x. So again, these are just all tweaks of the expression, tweaks of the equation, rewriting them using basic algebra, but you see that done. It just kind of, it's personal preference. But like I said, the original, there's nothing wrong with that. So it's, again, like I said before, if you check your solution in the solutions manual and they have something different than what you have, don't presume that you automatically did something incorrect. You may have the same correct solution. It may just be written in a different form, right? And that happens quite often with these, especially because there's so much going on in these equations. Okay. Now, as far as then writing the equation of the tan line, I trust you can do that. Now, notice here, though, here's our derivative y prime at the point 1, 2. So in this case, I would need to plug in both the x and the y, right? Normally, when we were finding equations of tan lines, we were looking for the slope. We found our derivative and we plugged in the x coordinate, but that was because the derivative was always just a function of x. So if I have to use implicit differentiation, I end up with a derivative that contains both x and y. Then in finding the value of that derivative, I would have to plug both of those in. Then once you get the value for that, that's your slope, and then you can write your equation from there. But I trust that you can write your equation of a tan line at this point, and so in this case, you would end up with a slope of 7/2 if you plugged 1 and 2 into that derivative. And then you go through your equation writing process, and you would end up with y equals 7/2 x minus 3 x. Okay, but equation of the tan line, that's nothing new. We've done plenty of that before. All right, so another example, number 4. I've got find dy dx for the equation y to the 5th plus x squared y cubed equals 1 plus y e to the x squared. All right, so again, just to give you some different examples. Okay. And like we said, with a lot of this stuff, a lot of it is organization and being neat, right? Not being messy with your work so you can keep track of everything. So find dy dx. So again, there's my first statement. I'm taking d dx at both sides of the equation. And then we get to the differentiation. So our derivative of y to the 5th. So by now we're kind of getting the hang of it. I'm differentiating with respect to x, so we follow our power rule. Derivative of y to the 5th is 5y to the 4th times the derivative of the base, which is y prime. Then I run into x squared times y cubed, so the derivative there is a product rule. So first times the derivative of the second. Now the second is y cubed, so again, power rule. The derivative of y cubed is 3y squared times the derivative of that base, which is y prime. So there's our first d second. Plus the second, which is y cubed, times the derivative of the first, x squared, whose derivative is 2x. And again, we're differentiating with respect to x, so we're done. But that's product rule with x squared y cubed. The derivative of the right side, well, there's again, derivative of a constant is 0, so derivative of 1. And then again, I run into a product. The derivative of y times e to the x squared, that is a product. So first times the derivative of the second. Now the second is e to the x squared, whose derivative for exponential function base e is the function, times the derivative of the exponent. Derivative of x squared is 2x. So that's chain rule with the exponential function. So that's our first d second. Plus second, which is e to the x squared, d first, well, the first is y, so its derivative is just y prime. That's the differentiation. And then once we're done with that, now we're just solving for y prime. Right? But all my differentiation is done. But be on the lookout for a lot of, product rule, chain rule stuff when you're doing implicit differentiation. Now it's back to basic algebra. I want to solve this thing for y prime. Now, first thing again, I'm going to rewrite it just to clean it up a little bit. So I've got this 5y to the fourth times y prime. That second term, I went ahead and cleaned up a little bit. I brought the 3y squared, 3x squared, y squared, and then y prime, just to rearrange the factors. Same thing with the second one, plus 2xy squared. Right, so again, I'm just kind of rewriting, making it a little bit neat and easier to keep track of everything. The right side, of course, I can drop the 0, and then again, I just rearrange the factors. I've got 2xy e to the x squared. And then the second term was e to the x squared y prime. That's fine. And then again, I think it just makes it easier to keep track of everything. So now we're going to focus on the y primes because that's what I want to isolate. So I would say we've got a y prime here, we've got a y prime here, and we've got a y prime here. So I want those terms on one side, so I went ahead and subtracted the e to the x squared y prime. Brought that over to the left, so 5y to the fourth y prime, 3x squared y prime, e to the x squared y prime. And I brought everything else over to the right, so 2xy e to the x squared that was already over there minus the 2x y cubed. And again, it's all going to follow the same basic process. You bring all the y prime terms to one side, factor out the y prime. What's left once you factor out the y prime? The right side is what it is. And then we just divide by that factor. So y prime then would be the right side divided by all of that. And, it's not uncommon that you see nice, pretty derivatives, right? Especially with implicit differentiation and these functions, that involve x and y. They don't always work out to be nice, neat little derivatives. So you can end up with things that look like that. Nothing wrong. Now I want to give you one example of doing this in the opposite direction. So everything so far has been dy dx, right? Where we were finding the derivative of y with respect to x, we were treating y as a function of x. But I told you earlier you could do that the other way as well. You could find dx dy. You could treat x as your output and y as your input. Derivative of x with respect to y, change in x with respect to y. Now, it doesn't change the differentiation process, of course, but it does change which variable you treat as the input and output. So now, no longer is y a function of x, but x is a function of y. And so basically everything is just going to get done kind of in opposite or in reverse with respect to the variables. So I'm differentiating with respect to y. So again, I'm going to dy both sides of this thing. Now, when I differentiate y to the fifth with respect to y, then there's our power rule, 5y to the fourth, times the derivative of the base, which is y, but since we are differentiating with respect to y, dy of y is now 1. Whereas up here, ddx of x was 1. All right, so you got to keep track of which variable you're differentiating with respect to. This is where you really know if you understand what we mean by the derivative and the notation that we're using. So then the second one again is a product of x squared y cubed, so I'm using product rule. But again, x is a function of y. So my first is x squared times the derivative of the second, which again I'm just using power rule, 3y squared, plus the second times the derivative of the first. Now again, since x is a function of y, then our derivative would follow the power rule, 2x times the derivative of the base. I went ahead and used x prime there just to be neater with the notation, but what does x prime represent? X prime represents dx dy. Right, because when we write y prime, that means dy dx. That means I'm looking at the change in y with respect to x. X prime then would represent the change in x with respect to y. Okay. Right side, derivative of the constant, that hasn't changed. We said the derivative of a constant is always 0. The rate of change there is 0. And then again, we've got the product rule for y e to the x squared. So there's our first y times the derivative of the second, which is e to the x squared, times the derivative of the exponent, which is 2x, times that derivative of x, which is x prime. Right. There's our chain rule. X is a function of y. Plus the second, which is e to the x, times the derivative of the first. Well, the derivative of y with respect to y, again, is 1. Next step, I just rewrote, put all this in one screen. I just rewrote everything, kind of cleaned it up. So there's the 5y to the fourth. I just rearranged some factors. Here I've got 3x squared y squared, 2xy cubed x prime. Right side, drop the 0. 2xy e to the x squared times x prime, just rewriting that first term, and the second term plus e to the x squared. And then we'll collect all of our, this time, x primes on one side. I've got an x prime there, x prime there. So I brought that to the left side, because now I'm solving for x prime. Everything else goes over to the right. Factor out the x prime. And then divide that right side by that factor. And there is x prime, which again is dx dy. Right. But of course, 99% of the time we're finding dy dx. And I want to show you an example of one where you're finding dx dy. It's purely arbitrary, in terms of which variable you differentiate with respect to. But because of our context, we're usually interested in dy dx. Slope of the curve, slope of the tan line. All right, at least one example there. Let's see, I have one other, if I can get this to hit the right button. All right, so I have one other example for you, just to throw in a trig function as well. So I've got the equation number 5. I've got 1 plus x equals sine of xy squared. So again, ddx of both sides, ddx of 1 plus x, ddx of sine xy squared. So there's our derivative of both sides with respect to x. Derivative of the constant, derivative of 1 is 0. Derivative of x with respect to x. And then we have the derivative of the trig function. And again, there's our chain rule. We say when we differentiate a trig function, what's the process? According to chain rule, the trig function is the outer function. So I differentiate the trig function, derivative of sine is cosine, with respect to its argument, times the derivative of the argument. And in this case, the argument is a product of x times y squared. So again, the process, differentiating a trig function with chain rule, the derivative of the function with respect to its argument. So derivative of sine is cosine of xy squared, times the derivative of the argument. And that's a product, so we're following product rule. First, which is x, derivative of the second, there's our power rule, 2 times y, chain rule, times the derivative of the base, y prime. Plus the second, well, I have a subtraction there, lost my sign. So first d second plus second d first. So our derivative of y squared of our first y squared times the derivative of the second, which is x, derivative of x is 1. Okay. And as soon as I wrote that subtraction the first time, I just left that and then just completely overlooked. So I'll fix that as we go through. But that is a product rule, right? So that's our first d second plus second d first. Now, since I then have to take this thing and solve it for y prime, the next couple of steps are all about just cleaning this thing up. So first, I just rewrote, the left side is 1, nothing happening over there. The right side, cosine of xy squared. Now just rearranged a little bit to clean up the right side. So there's 2xy y prime. Again, that should be plus y squared. Now, here, because I do have to eventually solve for y prime, which is stuck inside of these parentheses, there's a y prime right there. The first thing I then, or the next thing I then did was I distributed that cosine xy squared through these parentheses to clear those parentheses, so that we're left with just a bunch of terms, and then we can worry about isolating the y prime. So I've got cosine xy squared times 2xy y prime plus cosine xy squared times y squared. And now I've got a bunch of terms over there. The only y prime I have is the one that I have underlined. That's the only y prime. So what I did next was I just went ahead and subtracted that y squared cosine xy squared. And I just left the y prime term on the right side. So subtracting the y squared cosine xy squared. So I've got 1 minus that on the left side. Actually I have the minus there. And then the right side is 2xy cosine xy squared y prime, that term. And so again, all I'm interested in is the y prime. I can isolate that in this case, now directly dividing by that 2xy cosine xy squared. So there's the left side in this case divided by that factor, which leaves us with y prime. And so there's an example of one with a trig function. So kind of, and again, a reminder with trig functions, because I see a lot of mistakes made there. Chain rule says differentiate the trig function and then differentiate the argument. Don't do them at the same time. That's always the mistake I see made. I see them differentiated at the same time instead of just doing one at a time. All right, so that's implicit differentiation. Here's a new type of function that we haven't differentiated yet, at least. We've mentioned the inverse trig functions at some point. How do we find their derivative? Well, we haven't talked about them yet because we actually end up needing implicit differentiation in order to do it. So in order to find the derivative of the inverse trig function. Now, ultimately, all I care about is what these derivatives are. I'm going to show you why they are what they are, how they come about. But ultimately, like we did with the trig functions, you just have to know these. You're going to have to memorize them because there's going to be formulas for each one. So here's how we get the derivative of the inverse trig function. Now, first of all, recall from trig that when we say y equals the inverse sine of x, that is the same thing as saying that x is equal to the sine of y. Remember, y equals inverse sine of x means y is the angle whose sine is that, right? So y is the angle whose sine is x. X then is equal to the sine of y. Those statements are equivalent. Now there's also this little statement. I mentioned this to you before. When you talk about inverse trig functions, remember you have to restrict the angle. All right, and again, you may have to go back and look at your trig notes to remember why that was done, or look at why that was done. But there's a restriction on the angle, where this is true only for angles between negative pi over 2 and pi over 2 for the sine function. For the cosine function, it's 0 to pi, and for tangent, it's negative pi over 2 to pi over 2 non-inclusive. But that's a review of inverse trig functions, if you need to go back and look at that. But what that allows me to do then is, in order to then differentiate y equals inverse sine of x, I could differentiate x equals sine of y, because they're equivalent to each other. Okay? So again, I think I went up here and went somewhere. Maybe I didn't. I didn't. I have everything here. The only thing I wanted to add to that, was my initial statement, because I did leave that out here. So what's my initial statement? If I'm going to differentiate x equals sine of y, I'm going to use implicit differentiation here, which means I'm going to find d dx of both sides. So that's the only thing I didn't include here. All right. And so then we're using implicit differentiation to differentiate this equation. So there's our derivative of x with respect to x, which is 1. And then the derivative of sine of y, right? That's our chain rule. Derivative of a trig function is the derivative of the function. So cosine, derivative of sine is cosine of y, times the derivative of the argument, which would be y prime, right? Because we're finding d dx, derivative with respect to x. So then solving for y prime, I have that y prime, or dy dx, is equal to 1 over cosine y. Okay, so that's just taking that equation, solving it for y prime. Now we're going to do a little manipulation of that equation. I'm going to replace cosine y. Remember your Pythagorean identity. Cosine squared plus sine squared equals 1. I don't care what the argument is, as long as it's the same. So cosine squared y plus sine squared y equals 1. Which means then that cosine squared y is equal to 1 minus sine squared y. Just rewriting that equation. And then we can take the square root of both sides, and I can say that the cosine of y is equal to plus or minus the square root of 1 minus sine squared of y. Now, we've got a plus or minus in front of that square root, but in this case, I don't need the negative, because if you go back up to this, we said, remember earlier, that y was only, this applies only to angles between negative pi over 2 and pi over 2. Those would be angles in quadrants 1 and 4, correct? What are the values of cosine in quadrants 1 and 4? They're positive in both quadrants, right? Everything's positive in Q1. Cosine is positive in quadrant 4. Again, that's some trig review. That's why trig is so critical to this stuff. You have to remember your basic trig when you're working with these trig functions. So cosine is positive in Q1 and Q4, so since that's the only quadrants we're dealing with in this case, I don't need that. Right? So I only need the positive side of this. So I can then say that cosine of y is equal to the square root of 1 minus the sine squared of y. Right? But that's just, again, a Pythagorean identity. That's all that is. Now, the next thing I can do is say, well, wait. Look back up here where we said that x was equal to the sine of y. So where I have sine of y here, I can replace that with x. And so I get cosine of y equal to the square root of 1 minus x squared. Now I'm going to go back up to this statement, which said y prime was equal to 1 over cosine y. Right? We found that derivative. And now I can replace cosine y with 1 minus x squared. And I end up then with y prime equal to 1 over the square root of 1 minus x squared. Now again, ultimately all I care about is this, as long as you know what that is. But I want to at least show you where these come from. So for the function y equals inverse sine of x, the derivative y prime is 1 over the square root of 1 minus x squared. And you could follow a similar process for each of the inverse trig functions to get these derivatives. But again, all I really care is that you know what they are. So these are going to have to be committed to memory. The derivative of inverse sine that we just found is 1 over the square root of 1 minus x squared. Now do be careful with this. When we say x here, the x that you have there, the argument, is what gets plugged in here, right? I mean, so x is x. So whatever that argument is in the inverse sine function, that's what gets plugged into the formula for its derivative. Because that's what these are. We can call them formulas. So each of our inverse trig functions has a formula for finding its derivative. So the derivative of inverse sine is 1 over the square root of 1 minus x squared. Notice the derivative of inverse cosine of x is the negative of that, 1 over the square root of 1 minus x squared. Derivative of tangent, inverse tangent, is 1 over 1 plus x squared. The derivative of inverse cotangent, notice, is the negative of that, 1 over 1 plus x squared. The derivative of secant, inverse secant, is 1 over x squared roots of x squared minus 1. The derivative of inverse cosecant is the negative of that. So notice at least, there's really only 3 that you have to know. You need to know this one, you need to know this one, and you need to know this one. Because in the other three, the cofunctions are all just negatives of those. Make sure you especially know inverse tangent. The authors of this textbook love inverse tangent, so you're going to see that one pop up on a couple of different occasions. Okay, but you at least need to know those three. So the inverse sine, inverse tangent, inverse secant, and then the cofunctions are just the negatives of that. Now, we don't deal a lot with inverse trig functions in with respect to derivatives, but we do run across them on occasion. So we at least need to know what these are. But they're not certainly functions that we deal with on a regular basis. So with that said, we also don't want to forget about them either. You need to make sure you know these derivatives. So a couple of examples. All right, so here's the derivative of the function y equals the square root of the inverse tangent of x. Now again, you're just throwing in a new type of function. Everything else still applies. So I have to first recognize that that is a power function whose, it's a radical whose radicand just happens to be an inverse trig function. But that doesn't change the process. I'm still looking at chain rule here. I'm looking at that as a power function. So I've got inverse tangent of x raised to the 1/2 power. And then we follow our chain rule. So power rule, 1/2 times the base to the negative 1/2 times the derivative of the base. All right, that's our power rule. So apply power rule, 1/2 times the base to the negative 1/2, because I reduced the exponent by 1, times the derivative of the base, which is inverse tangent, who we just said its derivative is 1 over 1 plus x squared. And then again, I just rewrote it as always. I went ahead and dropped the inverse tangent to the denominator to give it a positive exponent. Then I put the radical back in as well. Okay, but like we keep saying with these, how much rewriting you do, that can change. Number 2, just to give you an example of what I was emphasizing earlier. Here I'm looking at the equation of the function y equals inverse cosine of 3x plus 4. So when I take the derivative of inverse cosine, which is the negative of 1 over the square root of 1 minus x squared, we said whatever I have here is what I plug in here. The argument gets plugged into the formula. So the derivative of inverse cosine of 3x plus 4 would be the negative of 1 over the square root of 1 minus that argument, 3x plus 4 squared. But then chain rule says we also then have to multiply times the derivative of the argument. Right? When I talked about chain rule in the last section, we said, trig functions, inverse trig functions, same thing. To differentiate those functions, you differentiate the function, which we've done. And then chain rule, we multiply by the argument, or the derivative of the argument. Which in this case, the derivative of 3x plus 4 is 3. All right? So again, that is coming from the derivative of the argument. All right, so it's the same process for trig functions, inverse trig function. What's the derivative of the function? For the inverse trig function, just make sure you're plugging that entire argument into the formula, and then we have to multiply times the derivative of that argument. Now notice all I did in the next step was just to put the 3 in the numerator. Notice I didn't bother multiplying this out or anything. That's fine. I mean, like we keep saying with this stuff, rewriting it, cleaning it up, but I don't want that to make it even uglier or be the main issue. So that's all that you really need to do there. That's fine. All right, that's the inverse trig functions. Again, those are going to have to be committed to memory, and you will see them pop up on occasion, especially in inverse tangent. You'll see that one more than any of the others, probably because it's the simplest one to work with, but don't neglect the others as well. Okay. That's it for that section.